Over the last number of days, we've been talking about charges that have been moving in external magnetic fields. Let's step back for a second and let's talk about charges that are, first of all, at rest. We've got a negative charge right here. It's at rest. It doesn't make a magnetic field. It doesn't make a magnetic field. Does it make a gravitational field? Yes, because it has mass. Does it make an electric field? Yes, because it has charge. So if it's at rest, it makes a gravitational field, it makes an electric field, it does not make a magnetic field. All right, let's expose that negative charge to an electric field, an external electric field. An electric field pointing downward. Does this negative charge that's at rest experience a force in this external electric field? Yes or no? Yes, you're right. Now, what direction is that force in the external electric field? I'm sorry? Yeah, good. It's toward the top of the page. It's opposite to the direction of the electric field, right? Doesn't have to be moving. Now, if it was moving downwards, upwards, to the left, to the right, it would still experience a force to the top of the page. Doesn't mean it would move to the top of the page, but it would still experience a force toward the top of the page. Now, let's put that negative charge that's at rest again in an external magnetic field. It experienced a force in the electric field, moving or not. Does it experience a force in the magnetic field if it's at rest? No, it's got to be moving. Okay? If it's not moving, it experiences a force in an electric field, but not in a magnetic field. If it is moving, does it experience a force in the magnetic field? Bit of a trick question. Bit of a trick question here. Who says yes? I shouldn't have told you it was a trick question. What are you saying there, Rutger?
I'm saying yes, but.
Okay, yes, but. I was going to say it depends. What's the but, Rutger?
It has to be moving in a particular direction.
All right. So it's got to be moving in a particular direction. If it's moving parallel to the field, either with the field or against the field, it doesn't experience a force, right? The force is zero in that case. If it's moving perpendicular to the field, then it does experience a force clearly. And if it's moving something other than parallel or perpendicular, it also experiences a force, but we don't have to deal with that force. It's a little bit odd, the direction and the magnitude of that force. Let's assume for a second that it's moving perpendicular to the field. Let's assume that it's moving towards the right side of the page. We want to determine the direction of the force here. Remember, in the electric field, it was easy. Negative particle experiences a force opposite to the field. In a magnetic field, a little bit harder. Got to use a hand rule for this. Which hand rule would you use? Wire grasp rule, coil rule, or would you use the hand rule for deflection? Good, it's the deflection rule. We're going to stick our thumb in the direction of the particle, which is towards the right side of the page. Fingers in the direction of the field, which is down the page. Remember, stretched out fingers, not bent. Okay, stretched out. Okay, palm's going to point out of the page. So my magnetic force in this case would be out of the page. My electric force right here is upwards. My magnetic force is out of the page. Got it? All right. What's the shape of the path followed by this charged particle that's moving through this external magnetic field, assuming it's perpendicular to the field? What's the shape of the path? It's going to be circular. And because of that, we can say not only that F is equal to QVB, which of course is a perfectly valid equation here, but because of that, we can also say that FC is equal to mv squared over r. Where do you find that equation on your data sheet? Yeah, you actually don't find it on your data sheet. You got to either take it from acceleration is equal to v squared over r, and then acceleration is equal to f over m, combine the two, or you got to remember it. Okay, if you remember it, be careful. I mentioned this the day that we learned this. Be careful you don't do this. Seems silly, but we do this sometimes. I've seen this a bunch of times over the years. Centripetal force is 1/2 mv squared over r. Clearly it's wrong. We all know that. Okay, but it's 2 hours into a diploma exam. You're a little bit stressed. Your mind's kind of a little bit mush, and it's easy to combine a couple equations like this. What have we done here? Okay, where does the confusion arise from here? Yep. Yeah, kinetic energy. And it's like, how can we possibly confuse kinetic energy with centripetal force? Because it's mv squared. Mv squared over r, 1/2 mv squared. Now, when we're sitting back here on a Monday morning and our mind is not necessarily all here because we've had a long weekend, but at least it's not mush because we've been writing a diploma exam for 2 hours, we can all see that this is wrong. Okay? Just be conscious of this, especially on tests and exams as you're doing it, not to do this. All right? So the shape of the path there is a circle. We can say F is equal to QVB. We can say F is equal to mv squared over r. And we can also say FC is equal to FM. Generally, if we're dealing with the shape of the path, the radius of the path, we're going to try this one. If we're not, we're going to try this one. But really, in all of those situations, all three equations are valid. So first one you try doesn't work, then try another one until you get something that works. Hey, quick little question for you. Go back to the electric field for a second. We know the shape of the path in the magnetic field is a circle. Does anybody want to take a stab? And we never talked about this with electric fields, but see if you can figure this out. Anybody want to take a stab at what the shape of the path of a particle will be in an electric field? I'll give you a hint. It's not a circle. What's the shape of the path of a particle moving through an electric field? That is, if it's moving perpendicular to the electric field, right? If it's moving this way. John? A curve? Yeah, you're right. It'll be a curve, but can we be more specific on that curve?
It either end up spiraling or
No. Yeah, it would be going. So if this is my electric field, the path of the particle is going to go up this way. Yes, Rucker, what shape is that? Yes. It's a parabola, right? When we did projectile motion back in physics 20, a mass moving in a gravitational field would follow a parabolic path. Remember, gravity and electricity are so much alike in just about every respect. If the shape of the path of a mass in a gravitational field is a parabola, then the shape of the path of a charge in an electric field is also a parabola. Does that make sense? All right. Let's take a few minutes here now, get our minds back into things by working on a few check and reflect questions. We'll give you 5 or 6 minutes here, maybe about 7 or 8 minutes here to work on these questions. Again, just to get your mind back in things. Then we'll work on a couple multiple choice questions, and then we'll move forward with some new stuff here this morning, okay? Page 601, here's the questions I want you to do. Number 3 to 6A, and then 7 to 10. So basically, 3 to 10, except for 6B. I'm going to take a look at a handful of multiple choice questions here right now, guys. First one is going to be, first two of them, I should say, multiple choice 75 and numerical response number 76. I'm going to ask you to submit those as multiple choice number 1 and numerical response number 1. Submit them together, please. Do these together this time as opposed to one at a time. It all goes with information about the Earth's magnetic field that you see right here. Just take note of this just for a second before you actually work on the question. What do you notice about the diagram? What do you notice about the diagram of the Earth's magnetic field? Yeah, north is at the bottom, right? South is at the top. That's what we talked about, right? We talked about that several times in class. Okay, this is just reiterating that, the fact that technically the Earth's magnetic field goes from north to south, and therefore magnetic south is in northern Canada, okay? So let's have a look at those two questions that goes along with this information. Submit them again as multiple choice 1, numeric response 1, as one response, and then we'll take a look at it in a couple minutes. Okay, guys, we're taking a look here. Number 75 says the protons in the solar wind experience a magnetic force which way? Hey, right away, we know the answer is going to be A or B. Look, if we've got a magnetic field that's pointing toward the top of the page, and it's kind of difficult to see on the board here that it's pointing toward the top of the page, but on your photocopied paper, I think you can. And even if you couldn't, you know which way the magnetic field points, right? Points towards magnetic south. Look, if it's pointing upwards and the particles are moving to the right, we know the force is going to be perpendicular to both of those, right? Perpendicular to the direction of the particles, perpendicular to the field. Now, if it was an electric field, now there's not an electric field surrounding the Earth, but if there was, if this was an electric field and pointing upwards, and the charged particles were moving this way, the positive charged particles are moving this way, we wouldn't have to do a hand rule for this, right? Positive particles would experience a force upward, and they would follow a parabolic path upwards. It's not an electric field. Okay, it's a magnetic field that's pointing upwards. So we know that these particles are going to experience a force perpendicular and then therefore travel on a circular path. Right hand, because it's positive particles, thumb in the direction of the particles, which is towards the right, fingers in the direction of the field. At that point, pointing upwards toward the top of the page, palm is going to point this way, out of the page. Make sense? So the answer for question number 75 would be B, out of the page, which most of you said. Good. 76. Assume that the velocity of the solar wind particles is perpendicular to the magnetic field. What's the radius of the circular path that the protons follow? Hey, look, we know that F is equal to QVB applies, F is equal to mv squared over R applies, and then FC is equal to FM applies. Since we've got the radius here, or at least we're looking for the radius, odds are we're going to start off with this. Okay, you could start off with any of the other two equations that are applicable when charged particles move through magnetic fields, but this is what's likely going to work for us. mv squared over r equals qvb. One of the v's cancels. We're left with mv over r equals q times b. Going to rearrange this. The r goes up by multiplying. The qb goes down by dividing. Swap places, basically. We're going to say r is equal to mv over qb. Okay, we got the mass of the alpha particle. The protons. It's 1.67, I think, times 10 to the minus 27. It's on your data sheet, anyways. The speed, is it given to us somewhere? Back here, yeah, 8 times 10 to the 5 meters per second. Okay, so we've got M, we've got V. The charge of the proton is 1.6 times 10 to the minus 19. And the magnetic field would be given to us back here as 1.10 times 10 to the minus 7 Tesla. Good? What does the answer work out to be when we do that? 759, for whatever reason, I'm thinking, is it 759, 7.59 times 7? Okay, I just had this vague recollection of, for whatever reason, of seeing this question, remembering that. 7.59 times 10 to the 4. So we'd express that as 7594. Because it's A decimal B, C times 10 to the D. If it was B times 10 to the W, we'd express that as what? B times 10 to the W would be 7.59. We'd put the decimal place in that case, right? Okay, let's take a look at, yeah, you know what? Let's take a look at one more question here. The question I want to look at now is 77. Don't worry about 78 here right now. It's just 77. Goes to this information on photon matter interactions. What's a photon? Yeah, it is a particle of light. But the point that I want to make here when I give you this question is that there will be some stuff that you read through here. We want to try to internalize everything and understand everything. But if there's terms you don't recognize, listen carefully. If there's terms you don't recognize, it doesn't matter. Does that make sense? If that happens on a diploma exam, I want you to think the same way. Okay, I want you to understand what you can. And if there's a definition that you need help with, then by all means, I can help you with that. But if you've never heard a term or a definition, I can promise you that you don't have to panic about it. It's not relevant to the question. Does that make sense? Okay, so let's see what we can do with that one. Number 77. All right, everyone. We've got most of you having responded here. Most of you have actually picked A. About 70% of you have picked A, but we've got some answers kind of all over the place on this. We've got a few people picking B, a couple of people picking D, and then 5% of you saying we're not sure what the answer is. So let's take a look at it here. says curve pass in the particles in the pair production diagram. Let's go back to the pair production diagram first of all and try to see what's going on here. Talks about these photon matter interactions. We know what matter is, right? Matter is anything with mass. So it's what you're looking at right now, basically anything but energy. A photon is a particle of light. So if you visualize the flashlight as firing off tiny little particles of light, and then we're kind of all seeing all those together as the light that we see. That's what a photon is. It says when a photon passes through matter, so when light passes through matter, it interacts with the atoms and their electrons. There are 4 important interactions with matter that this photon can undergo. Okay, interaction number 1, the photon may be scattered, and the electron by the electron in the process and lose some energy, transferring momentum and energy to the electron. So you can picture this little particle of light going in, being scattered or deflected by the electron and losing some energy and momentum in the process. In other words, the electron takes away some of the energy and the momentum. Observation number 2, the photon may move an electron out of an atom, and in the process the photon disappears. So the photon, again, you're visualizing this little particle of light. It gets absorbed, and all of a sudden, photon's gone. The electron has left the atom, had to get energy from somewhere. Well, it got energy from the photon, right? But now the photon's gone because the electron took all of the energy away. 3, the photon may move an electron to a higher level, and in the process, the photon disappears. So it's kind of like number 2. 2 and 3 are almost the same. The photon, it gets absorbed by the electron. If it's got enough energy, it can cause the electron to jump out of the atom. If it doesn't have enough energy, it can just cause the electron to jump to a higher level. Okay, but in either process, the photon disappears. And finally, number 4, a photon may actually create matter. So light may make matter. The most common process called pair production. Okay, we don't know what that is, but they're explaining it to us, right? It's the production of an electron and a positron. What's a positron? By the end of the year, we'll have talked about positrons. You'll know what a positron is. Okay? But I've told you, if you haven't heard a term before, if I haven't taught you a term, I can promise you it's not relevant. So by the end of the year, you will have learned about positrons. Maybe you get a question on positrons where it is relevant, but right now it's not particularly relevant, other than knowing the positron is positive, which they tell us right here. It's a positive particle. It's actually antimatter, the antiparticle of an electron. It has the same mass as an electron, but it has the opposite charge. In addition, a massive particle such as an atomic nucleus, electrons, positrons, same mass, much lighter than a nucleus. It must gain some of the photon's initial momentum. All right, so here's a diagram here. Here you got your photon, this particle of light, okay, that's striking it here, and then what happens? You're producing both a positron and an electron. The positron seems to be deflecting upwards like this, and the electron seems to be deflecting downwards like this. Hey, it should make sense to us, I think, that they're deflecting in opposite directions. Why? They're opposite charge. If you got a magnetic field here that's causing them to deflect, a positive charge will deflect one way, a negative charge will deflect the other way. All right, we want to know which way the magnetic field has to be in order to cause this deflection. If we take a look at this, the options here, I'm going to eliminate C and D right away. Okay, why? Why could I eliminate C and D right away? How do I know that they can't possibly be the answer before I do any kind of analysis here? Lewis? Good. They would be parallel to the way the particle is moving. Look, the particle is moving to the right. If you have a field that's to the right or to the left, there will be no force on either one of these particles. So it can't be C or D. It's got to be either into the page or out of the page. Now, how do you know whether it's into the page or out of the page? Which hand rule are you going to use? Wire grasp rule, coil rule, or deflection rule? Which hand rule do you want to use? Which hand rule is it? Is your hand kind of moving there, or are you just kind of grabbing your water bottle? Oh, you can still answer the question. Yeah, it's the hand rule for deflection. Good. Now, is it right hand rule or the left hand rule for deflection? Use either, depending on what? Depending on which particle you're choosing, right? Now, it doesn't matter whether you choose to use the electron or the positron here, you just got to be consistent with that. Okay, if we're using the electron, okay, the electron is deflecting downwards like this. We're going to say that, okay, left hand, thumb in the direction of the particle, which is towards the right. The palm must point in the direction of the field, which is downwards. That means, sorry, the force, I should say. That means the field is going to point into the page. What if we had to pick the positron? Well, the positron is deflecting upwards. I'm going to use my right hand for this. Right thumb in the direction of the particle, which is towards the right. Palm's going to point upwards, because that's which way the force has to be to cause it to deflect upwards. Fingers are going to point, once again, into the page. So any way you look at it, the magnetic field's got to be into the page there. Does that make sense? Okay, I like this question. I really like 77. Okay, we took a look at a question here a few minutes ago, number 75, where we were asked to find the direction of the magnetic force on this charged particle. Okay, same question, really, as what we had here. This one just kind of stepped it up a little bit in terms of all the wording around it and the concept around it, right? This one we had to work through some more stuff in our minds. But when it came down to it, it's the exact same concept, and we do the exact same thing, right? Yep. Yep. All right.